For our final set of topics, we are going to return to our pure n-body system, that is, a system of n point masses interacting via gravity alone, and we're going to try to tease out a bit more analytical understanding of the long-term processes that take place in these systems. Much of the analysis presented here is going to be geared towards the understanding of the solar system and other planetary systems or moon systems, collections of large naturally occurring bodies on mostly stable orbits, or the interaction of small point masses or test particles representing asteroids and smaller bodies with these natural systems over very long periods of time. However, many of these concepts can be ported over towards understanding of deep space spacecraft orbits and can also be used in some cases as design tools. Much of our derivations are going to follow those presented in Murray and Dermott's Solar System Dynamics book, in particular chapters 6 through 9, and we will frequently refer to that work for specific examples and results. We start by considering, once again, the disturbing function. Recall that the disturbing function represents the perturbation on the orbit of a mass m2 about a central body m1 due to n minus 2 external or internal perturbers. The differential equations representing this m-body system take the form of our standard two-body equation here on the left-hand side and the perturbations due to all of the perturbing bodies on the right-hand side. Each argument within the summation on the right-hand side represents the perturbation on the orbit of body 2 due to body j. And it has a term that is the position of j with respect to the central body, and another term that is the position of body 2 with respect to body j. The entire summation is a specific perturbing force, and as it is a conservative force, it is equal to the gradient with respect to the position of body 2 of some function r, and it is this r that we call the disturbing function. We can write the disturbing function due to body j as gmj, or the gravitational parameter of j, sometimes written as mu sub j, times the quantity 1 over r2 rel j, which is the norm of the vector r2 rel j, minus r2 rel 1 dotted into rj rel 1 over the norm of rj rel 1 cubed. We call this first term the direct term, and this second term the indirect term. And this nomenclature is due to the fact that the indirect term arises solely due to the choice of coordinate origin. If we express everything with respect to the common center of mass of the whole n-body system, then we wouldn't get these indirect terms. We would just have a collection of things that look more or less like the direct terms. We have also previously shown that we can expand each of these r sub j's, which, remember, represent the perturbation on the orbit of m2 due to each of the perturbing bodies mj, in an infinite series in the Legendre polynomials with argument of cosine alpha j, where alpha j is the angle between r2l1, the orbital radius vector of body m2, and the orbital radius vector of the jth perturbing body, rjl1. We will now consider the case of two smaller bodies, m2, m3, both orbiting a central mass m1. We know that for any point in time, we can fit a two-body orbit to the path of m2 and m3, and we can define osculating orbital elements for each of those. And so everything on this slide that is an orbital element with a subscript should be interpreted as the osculating orbital elements of that body. That is, a sub 3 is the osculating semi-major axis of m3. We now have two disturbing functions, r2, which represents the perturbation on m2 due to m3, and r3, which represents the perturbation on m3 due to m2. As in the previous slide, each of these has a direct and an indirect term of these forms. Our eventual goal here is to expand these disturbing functions in series in the orbital elements of the bodies. In order to do that, we have to make quite a few substitutions and take a few intermediate steps, but always keep in mind that what we're going for here is that at the end of the day, we wish to write an infinite summation representing the disturbing functions of each of these bodies. We will then analyze the reading terms of that infinite summation in order to see whether we can gain a better analytical understanding of the long-term effects of these mutual perturbations. Our first step is to define this RD term, which will be the same for the direct terms for each of these two disturbing functions. RD is defined as the osculating semi-major axis of body 3 divided by the magnitude of R3rel2, that is the distance between bodies 2 and 3. And then we will have two terms for the indirect terms of each of these perturbing functions. R sub e representing an external perturber, and R sub I representing an internal perturber. So the assumption here is that the orbit of body 2 lies inside of the orbit of body 3. Therefore, M3 is acting as an external perturber on M2, and M2 is acting as an internal perturber on M3. RE and RI are defined as so, and when we plug them back into their respective disturbing functions, they have to have slightly different leading terms, as shown here. What these substitutions have gotten us so far is that we have the same R3rel2 term in both of the direct terms of each of these disturbing functions. We've seen this before. We know that from the law of cosines, we can write the reciprocal of the norm of R3rel2 is equal to the square root of R2rel1 squared plus R3rel1 squared minus twice R2rel1, R3rel1 times cosine alpha, where again, alpha is the angle between those two vectors, between R2rel1 and R3rel1. Our goal is to expand the disturbing function in our osculating orbital elements. And so we need to get rid of this alpha and replace it with something that maps to the orbital elements. We do so by introducing this capital psi quantity. Capital psi is going to be defined as cosine alpha minus the cosine of the difference between the true longitude of body 2 and the true longitude of body 3. Recall that the true longitude is the sum of the true anomaly plus the argument of periapsis plus the longitude of the ascending node. We have also previously defined the sum of the argument of periapsis and the longitude of the ascending node as the longitude of periapsis, given by this varpi symbol. So the true longitude can also be thought of as the sum of the true anomaly and the longitude of periapsis. We substitute psi into our law of cosines expression, where it simply replaces the cosine alpha with cosine L2 minus L3 plus psi. If you plug this definition into here, you'll see that this all evaluates to just cosine alpha again. And then we can expand this in Taylor series. Remember that in general, a Taylor series expansion of some function f of x about a point A is given by the infinite summation over index n equals 0 to infinity of the nth derivative of the function evaluated at A divided by n factorial times x minus a to the nth power. We expand this expression in psi, and we get this summation, which you should 100% check. Here, this R0 value is defined as R2rel1 squared plus R3rel1 squared minus twice R2rel1, R3rel1 times cosine of that true longitude difference, all square rooted. We still wish for this expansion to be in terms of the body's orbital elements. And so to facilitate this, we are going to define a new quantity. Rho naught will be defined as A2 squared, that is the osculating semi-major axis of body 2, plus A3 squared minus twice A2, A3 times cosine of the true longitude of body 2 minus the true longitude of body 3, all square rooted. If we Taylor expand this last term of this summation in rho naught, then we can write that is r naught to the negative 2n plus 1 is equal to rho naught to the negative 2n plus 1 plus the infinite summation over index m from 1 to infinity. We don't have a 0th order term here because that folds into this leading term there. This infinite summation will be of R2rel1 minus A2 to the mth power times the mth partial in A2 of rho naught to the negative 2n plus 1 plus R3rel1 minus A3 to the mth power times the mth partial in A3 of rho naught to the negative 2n plus 1. At the same time, we can write this term, rho naught to the negative 2n plus 1, as a3 to the negative 2n plus 1 times the quantity 1 plus the ratio of a2 to a3 squared minus twice that same ratio times the cosine of the difference of the true longitudes of the two orbits, all to the negative n plus 1/2 power. And the reason why we want to express this in this particular form is that this allows us to bring to bear another piece of mathematical formalism known as the Laplace coefficients. We can rewrite this expression as rho naught to the negative 2n plus 1 is equal to a3 to the negative 2n plus 1 times 1/2 times the infinite summation from j equals negative infinity to infinity of the jth bn plus 1/2 Laplace coefficient with argument a2 over a3 times the cosine of j times the difference in the true longitudes of the two orbits. So what are these Laplace coefficients, which are not to be confused with Laplace's coefficients, which are an entirely different thing altogether? Laplace coefficients come from Laplace's 1798 work, which tells us that if we have an expression of the form 1 minus xz to the negative s times 1 minus x over z to the negative s, we can express this as 1/2 of the infinite sum of the b sub s Laplace coefficients with argument x times z to the j. S must be of the form I plus 1/2, where I is a positive integer. So first, let us demonstrate to ourselves that our particular expression actually does fit this form, and then we'll return and talk about what the Laplace coefficients are and what some of their useful properties are. We have this argument, 1 plus a2 over a3 squared minus twice a2 over a3 times cosine of L2 minus L3. We can rewrite this as 1 minus a2 over a3 times e to the I times L2 minus L3. E here is Euler's number, so this is the complex exponential, all times 1 minus a2 over a3 times e to the negative I times L2 minus L3. Remember, e to the ix is the same as cosine x plus I sine x. When we expand this product, the imaginary parts of the exponential terms cancel, and so we're left with just our original cosine term. This product exactly matches this form, and so we know that we can apply the Laplace coefficient formalism. Laplace coefficients are the coefficients of a Laurent series, and they are formally defined as follows. 1/2 of b sub s j with argument x is equal to 1 over 2 pi times the integral from 0 to 2 pi of cosine j psi over 1 minus 2x cosine psi plus x squared to the s integrated over psi. The solution to this integral is given by the product of s times s plus 1 all the way to s plus j minus 1 over j factorial times x to the j times the hypergeometric function f21 with arguments s, s plus j, j plus 1, and x squared. A hypergeometric function is related to the hypergeometric series and is formally defined as the solution for a second-order linear ordinary differential equation, but it pops up in a lot of different contexts, and it's a very useful thing that your computer can crunch very efficiently for you. Some useful attributes of the Laplace coefficients are that the negative jth coefficient is equivalent to the positive jth coefficient, and that the derivative in x, the argument of the coefficient, can be given recursively as s times the jth minus 1 coefficient of s plus 1 minus twice x, the jth coefficient of s plus 1, plus the jth plus 1 coefficient of s plus 1, the arguments for all of these still being x. Similarly, we can write the nth derivative in x of the Laplace coefficient. It has this form, and we have another recurrence relationship of this form, which allows us to generate long series of these Laplace coefficients fairly efficiently, which we need because this summation literally contains an infinite number of them. We will actually be using only a finite set of these, but even so, it is important for us to be able to efficiently generate them. If we now put all of this together, we can write the direct part of the disturbing function, that RD term, as this infinite summation, which is actually a summation over three other summations. So let's backtrack a little bit to ensure that we understand how we got here. This outermost summation in index n comes from our original Taylor expansion of this denominator term. The inner summation in J from negative infinity to infinity comes from our use of the Laplace coefficients to represent this rho naught to the negative 2n plus 1. It is this summation. It itself is summing over another infinite summation over index m. That comes from our Taylor expansion of the R naught term, this term here. And finally, we have a new innermost summation over a new index k, which allows us to use this compacted notation in order to package everything together. And so this innermost summation is from k equals 0 to m of m choose k times epsilon 2 to the k times epsilon 3 to the m minus k, where epsilon is defined as the orbital radius magnitude of body I scaled by its oscillating semi-major axis minus 1, all times this four-dimensional coefficient matrix A sub n j k m minus k, which is defined as follows. These coefficients are what is mapping us back to this expression here, this infinite summation over m in the mth partials of rho naught to the negative 2n plus 1. This in turn gets replaced by this series, and so here we see the various orders of the summations. So it definitely takes some very, very careful bookkeeping to unpackage all of this and to make sure that everything is self-consistent, but it's a worthwhile exercise because it really allows you to see what is happening from start to finish. Again, let us not forget our ultimate purpose. We want to write expansions of the disturbing functions in terms of the orbital elements, so that we can then see the effects of the dominant terms, should there be dominant terms, on the evolution of the orbits of our interacting bodies. Remember, this is only the direct part of the disturbing functions. We still have the indirect parts, those external and internal perturbation terms, but those are functions of alpha only. And so for those, we need to only expand in alpha, which was the angle between our 2L1 and our 3L1. And we've already done this. We do this via the Fourier-Bessel expansions of true anomalies. As we've done countless times before, we express the orbital radius of either body in terms of its Keplerian orbital elements, which gives us this matrix multiplied by the orbital radius magnitude. Cosine alpha is R2L1 dotted into R3L1 scaled by their magnitudes. And when you plug in this form in terms of their Keplerian orbital elements into this expression, what you get is this long series of products of various trigonometric terms. But all of these trigonometric terms have the same basic arguments. The arguments are either the summation of the true anomaly and the argument of periapsis for each of the two bodies, the inclination by itself of each of the two bodies, or the difference in the longitudes of the ascending nodes of the two bodies. That's it. Everything is repeated again with only these three things happening. The sign of the true anomaly is given by the Fourier-Bessel series of this form, and the cosine of the true anomaly is similarly given by a Fourier-Bessel series of this form, where J sub s is a Bessel function of the first kind.